We will now take a look on how to obtain better filters and longer filters, extending the length of the MDCT, but without having an impact on the system delay. So longer filters, they are obtained with high order polynomials in the polyphase matrix. Our approach is to obtain easily invertible polyphase matrices. So we want to multiply the MDCT polyphase matrix with more easily invertible matrices with polynomials of first order. To control the resulting system delay, we will design different matrices with different needs for delay to make them causal. So if we take, for example, the MDCT polyphase matrix with a general window function, not necessarily the sine window, we can call this the polyphase matrix HMDCT, much more general, and this matrix contains polynomials of first orders. Then we can multiply it with another matrix of polynomials of first order, for example, LZ. So this matrix LZ needs to have a form such that again results in a modulated filter bank, and we need to preserve the diamond shape of the matrix. We can have the zero delay matrix. This is a matrix that fulfills this condition. Its inverse is causal, hence we do not need a delay to make it causal. It's already causal, and still increases the filter length. So observe that since the matrix has a causal inverse, it can increase the filter length of the resulting filter bank without increasing the system delay. Hence it adds zeros inside the unit circle. The coefficients h of n and l, they don't affect the delay or the perfect reconstruction property, but the frequency response of the resulting filter bank. So what we want is to improve the frequency result of the filter bank, but without affecting the perfect reconstruction and without adding more delay. So in this case, the coefficients, they need to be found by numerical optimization. Another type of matrix that we are going to use is the maximum delay matrix. In the maximum delay matrix, we have that this its inverse need a delay of 2 blocks to make it causal, hence it adds zeros outside the unit circle. So our design method would be that we will determine the total number of the zero delay matrices and maximum delay matrices according to the desired filter length. And we will determine the number of the maximum delay matrix according to the desired system delay. And then we determine the coefficients of the matrix through numerical optimization to optimize the frequency response. So this is our strategy. We determine the total number of zero delay matrices and maximum delay matrices according to the desired filter length. We determine the number of maximum delay matrices according to the desired system delay, and we determine the coefficients through numerical optimization. One example here that we have is, for example, for 128 subbands, we have in the dashed line an orthogonal filter bank with the filter length of 256 and the system delay of 255 samples. And we also have the solid line now with it's a low delay filter bank, and it has a length of 512, so it's 2 times more than the dashed line, but we have a system delay equals of 255. So we have a low delay filter bank that has longer filters but with the same overall system delay. You can find more information about low delay filter banks and optimization of filter banks and determine the coefficients of filter banks using optimization in the lecture Multirate Signal Processing. It's also offered by Professor Schula at the Humana University of Technology, and there we go through different aspects of optimization, and we also go through the aspects of low delay filter bank, so you can take a look at the multi-rate signal processing lectures. Now we'll go through a real-time example using a low delay filter bank, and basically it's based on the previous example of this fast implementation of the MDCT with some few modifications. So we'll import and use the same libraries that we used before. We have the same initialization for the matrices we are going to use. We are going to use the delay matrices, the G matrix, the H matrix like we did before. We don't have changes in the delay matrices. We still use the symmetric F matrix for the multiplication of the samples with coefficients. We also have the sim F inverse matrix that we've seen before. We have here now a G matrix. This is the implementation of a matrix G, and we have the inverse of the G matrix. We have the H matrix, the inverse of the H matrix. We still use the DCT4, but now we will have here some differences. So here we will have our coefficients, and we will have a G0 coefficient, so the G0 matrix, and a G1 matrix. So those are we didn't see previously. And also our FB, our filter bank coefficients, they are not the sign window, they come from an optimization. And here we now have that we have the output. It goes through, we have this multiplication of the samples with the coefficients. Then we have this G matrix with the G0 coefficients. Then we have the G matrix with the G1 coefficients here. And then we have the DCT4, and we are returning the variable y. And here the same is in the synthesis side. We have this low delay filter bank inverse, and we have here the G0 coefficients and the G1 coefficients, and we return the reconstructed signal. So now what we are going to do is we are going to load this pre-optimized coefficients from a file. So you can take a look into a multi-rate signal processing and how to generate this optimized coefficients. And you can use, for example, other languages. You can use Python, you can use Octave, MATLAB, or whatever you want. So this is also one big difference that we have in this example. Then here we will have this part here that we assume a symmetric F matrix, so the determinant is equals to 1, and we only need the first n coefficients of F and not the 2 times capital N coefficients. So this is what we are doing here. And then the example goes as we did before, and here again we are having a plot of the subband 0 in the system low delay filter bank, and we have here the low delay filter bank impulse response of subband 0 of the synthesis, and here the enlarged magnitude frequency response. So now this is the same example like we did for the fast implementation of the MDCT, but now we are using this low delay filter bank implementation using delay matrices, maximum delays, minimum delays, and we also have the coefficients of the filter bank given by numerical optimization, and you can refer to the multi-rate signal processing to see how to obtain this. And then we will exactly the same. We use PyAudio. We have a GUI to control. We are doing threads. So the example is exactly the same, but we are just changing the approach, and now we are using the low delay filter bank approach with different matrices. Hello, here we have our example running, and it's the MDCT implementation using a low delay